Hello everyone. In this video, we are going to find all polynomial f mapping complex number into complex numbers such that f of z squared minus z equal to fz times fz minus 1 for all complex number z. To solve this problem, first we will observe the character of the roots of the polynomial f. If a is any roots of polynomial f, by the definitions of roots we have fa equal to 0. By replacing z with a, we have fa squared minus a equal to 0. And by replacing z with a plus 1, we have fa squared plus a also equal to 0. These two equations tells us that a squared minus a and a squared plus a are also roots of f. So we have this statement. This statement tells us that we can always construct two new roots from the old roots. These two new roots may be the same with the old roots or may be different with the old roots. So we can divide the polynomial f on the problem into three cases. F has roots, f doesn't have roots. F has roots can be divided into two cases. First, f has non-zero roots. Second, f doesn't have non-zero roots. F doesn't have non-zero roots equivalent with f only has 0 roots. So we have these three cases. For the first case, suppose that b not equal to 0 is root of polynomial f. By the statement inside the yellow box, we have b squared minus b and b squared plus b are also roots of polynomial f. By observing the maximum value of modulus of these two roots, we have maximum of modulus b squared minus b and modulus b squared plus b equals to modulus b times maximum of modulus b minus 1 and modulus b plus 1. Since b not equal to 0, then one of these two quantity must be greater than 1. So this quantity greater than modulus of b. So basically from this statement, we can always construct new roots which one of them has greater modulus than the old roots. Because we can construct new root with greater modulus, we can construct another root with more greater modulus. All of this argument can be used repeatedly, which means f has infinitely many roots. The only polynomial that has infinitely many roots is only f equal to 0 everywhere. And of course, this function is satisfying the functional equations on the problem. For the second case, f only has 0 roots. The only polynomial that only has 0 roots must be in the form of fz equal to c times z to the power of k, which k is natural number and c not equal to 0. By substituting this fz into the functional equations on the problem, we have these equations for any complex number z. So we have c equal to c squared, which means c equal to 0 or c equal to 1. Since c not equal to 0, we must have c equal to 1, which means fz equal to z to the power of k. And of course, for any natural number k, this fz is satisfying the functional equations on the problem. For the third case, f doesn't have roots. The polynomial that doesn't have roots must be in the form of fz equal to a constant, which the constant is not 0. By substituting this fz into the functional equations on the problem, we have c equal to c squared, which means c equal to 0 or c equal to 1. So we have c equals to 1 since c is not equal to 0. So we have fz equal to 1. So from all of these three cases, we can conclude that all the solutions are fz equal to 0, fz equal to 1, and fz equal to z to the power of k, which k is natural number. And there we are done.